everybody. In this video we're going to talk about expanding binomial powers a little bit before we talk about the binomial formula and all of its greatness. So what does it mean to expand a binomial power? Well, that's like when we take something like this, x plus y to the fifth, and we multiply it out, x plus y times x plus y times x plus y times x plus y. Okay. Now, this would be a lot of work to do by hand. So let's go back a little bit for a minute and look at expanding powers of a plus b, or in the similar thing we had x plus y, raised to the n. There's a pattern that's going to emerge. X plus y to the 0 is just going to be 1. X plus y raised to the 1 power, so just multiplied by itself once, or not multiplied by anything, right? It's just x plus y. X plus y squared is 1x squared plus 2xy plus 1y squared. X plus 3y cubed is equal to 1x cubed plus 3x squared y plus 3xy squared plus 1y cubed. X plus 4 to the 4th follows a similar pattern. And x plus y to the 5th follows another similar pattern. Now, where are these numbers all coming from? We can get them from a cool little triangle, and that is called Pascal's triangle. How is this triangle formed? Well, we can put a whole bunch of ones down, and then we get to the next row by adding the numbers. So 1 plus 1 leads to 2. 1 plus 2, we get 3. 2 plus 1, we get 3. 1 plus 3, we get 4. 3 plus 3, we get 6, etc. Now, we were worried or curious about x plus y to the 5th power. That 5th power correlates to this line right here, which happens to be the 1, 2, 3, 4, 5, 6th line, because we started at x plus y to the 0 power. Okay, so the coefficients of my values for x plus y to the 5th are 1, 5, 10, 10, 5, 1. But the powers have to all add up, and each term have to add up to 5. Okay, but how many terms are there? There's 1, 2, 3, 4, 5, 6 terms. Alright, so keep that in mind, and we're going to do an example real quick. So let's talk about this case where we have a 3 in front of the y. How is that going to be different? What are we going to do differently? Well, the coefficients of the 6th row of that triangle will give me the coefficients, part of the coefficients that I need for this expansion. Those coefficients, if you remember, are 1, 5, 10, 10, 5, and 1. And why am I using the 6th row? Because I have it raised to the 5th power. So if this were, instead of x plus 3y, if it were a plus b raised to the 5th power, I would simply have the coefficients 1, 5, 10, 10, and 1, so that 6th row, and then I would multiply by a to the 5th power. So I start my first term raised to the power that I have, then I multiply by the second term raised to the power of 0. So what do my powers add to? They add to 5. And then I'm going to add a raised to the 4th power, so I reduce the power of a and I increase the power of b. And I keep doing that. A cubed, b squared plus a squared b cubed. And I forgot one of my coefficients. I forgot 5 here. So this is plus 5 a to the 1 b to the 4th plus 1 times a to the 0 b to the 5th. So you can see all my exponents in each term are going to add to the correct numbers. But in place of a, I have x. And in place of b, I have 3y. So I'm going to have 1 times x to the 5th times 3y to the 0 power plus 5 times x to the 4th plus 3y to the 1st power. And then I'm going to continue. So anywhere I see a, I'm going to put x. Anywhere I say b, I'm going to put 3y. Now let's continue this down. 10 times x squared, 3y cubed, plus 5 x to the 1, 3y to the 4th, plus 1 x to the 0, b to the 5th. After some reducing, all the zeros, those go to 1, and it's raised to the 0, it's just 1. So I will get x to the 5th plus 15 x to the 4th y plus 90 x cubed y squared plus 270 x squared y cubed plus 405 x y to the 4th plus 243 y to the 5th. Now this is all great and nice, but what happens when we have something bigger? Something like this, raised to the 40th power. I don't want to go and use that triangle, find the 41st row, and then multiply all that out. Okay? If I want to find one term of this, then I can use another trick. And that is what is called binomial coefficients. We evaluate them as n factorial over r factorial times n minus r factorial. We read it as n choose r. And why is this important? Why is this nice? Because it relates to the Pascal's triangle. Let's see that relation. Pascal's triangle coefficients are in the top 0 choose 0, which is 1. 1 choose 0, which is 1. 1 choose 1, which is 1. 2 choose 0 is 1, etc. So we get our Pascal's triangle here. Let's look at it. 1, 1, 1, 1, 2, 1, 1, 3, 3, 1. You can see that pattern, etc. So we're going to use the binomial coefficients and talk about the binomial theorem, which we'll do in another video.